Welcome to the course, A Foundation for Machine Learning and Data Science, section Linear Algebra Overview. In this section, we will be covering the language of data such as what is a scalar, what is a vector, what is a matrix, the types of matrices, the matrix operations and matrix of factorization, the types of regression problems, and the types of classification problems that we will be dealing with in machine learning. First, let's see what's linear algebra. Linear algebra is a branch of mathematics and it's also called the mathematics of data. Scalars, vectors, and matrices are the language of data in linear algebra. Linear algebra is about linear combinations and is the study of lines and planes to the least. Knowledge of linear algebra is the basic requirement for learning statistics. It's a prerequisite for a deeper understanding of machine learning. Scalar. A scalar is a real number. It can be an integer or fractional, that is float, or positive or negative, etc. Here are some examples. This scalar has an integer value, this scalar has a floating point value, and this scalar has a negative value. Vector. A one-dimensional array or a list or a column of scalars usually represented using lowercase letters. Example, V equal to V1, V2, V3, where V1, V2, and V3 are scalars. All basic mathematical operations such as additions, subtractions, multiplications, divisions, and dot product can be performed on vectors, and the dimensions of the vectors must be the same to perform any of these operations. Here are some examples. A vector can have either one row or one column of elements because it's a one-dimensional array. Matrix. A two-dimensional array of scalars with one or more rows and one or more columns, usually represented using uppercase letter. All basic mathematical operations except the dot product can be performed on matrices, and the dimensions of the matrices must be the same to perform any of these operations. To perform the dot product operation, the number of columns n in the first matrix A must be equal to the number of rows n in the second matrix B. Consider the multiplication of these two matrices A and B. The matrix A with the number of rows m and the number of columns n is multiplied with the matrix B with the number of rows n and the number of columns k. The resultant matrix C will have the number of rows m and the number of columns as k. Here is an example of a matrix with 2 rows and 3 columns. Let's see the different types of matrices available. Square matrix. A matrix where the number of rows n equals the number of columns m, that is, n is equal to m. This is an example of a 3 by 3 square matrix. Symmetric matrix. A type of square matrix where the top right triangle is the same as the bottom left triangle. Like this. The axis of symmetry is always the main diagonal of the matrix from the top left to the bottom right. A symmetric matrix is always square and equals to its own transpose, denoted by its own transpose. Example, A equal to transpose of A. This is an example of a symmetric matrix. Triangular matrix. A type of square matrix that has all values in the upper right or lower left of the matrix with the remaining elements filled with 0 values. A triangular matrix with values only above the main diagonal is called an upper triangular matrix. Like this. A triangular matrix with values only below the main diagonal is called a lower triangular matrix like this. Diagonal matrix. A matrix where values outside the main diagonal have a zero value. In other words, diagonal matrix is equal to both upper and lower triangular matrix together. Like this. A diagonal matrix may be represented as a full matrix like this, or as a vector of values on the main diagonal like this. Identity matrix. A square matrix in which all the elements of the principal diagonal are ones and all other elements are zeros like this. Now let's see some of the common matrix operations. Matrix transpose. Matrix transpose creates a new matrix with the number of rows and columns are flipped. They are denoted by the superscript T. Example, C is equal to transpose of A. Basically, the rows become the columns and the columns become the rows like this. These 3 rows have become 3 columns here, and 4 columns here have become 4 rows here. So this is an example of a transpose matrix. Matrix inversion. Matrix inversion creates a new matrix by inverting the original matrix. Not all the matrices can be inverted. The matrix should be square and the determinant should be non-zero. They are denoted by the superscript -1. Example, C is equal to A to the power of -1. The matrix inversion involves some mathematical calculations, and let's not get into the details of it here. This is an example of matrix inversion. Matrix trace. Matrix trace is the sum of the main diagonal elements of the matrix like this. Here the sum of the main diagonal elements are 1 plus 5, 6 plus 9, 15. It's also good to have a basic understanding of matrix factorization. A deeper understanding of it is not needed for this course. Matrix factorization, also known as matrix decomposition, is a way of reducing a matrix into its constituent parts, that is, decomposed matrices. It's an approach to simplify complex matrix operations that is performed on the decomposed matrix rather than on the original matrix itself. I would like to give an analogy here. Matrix factorization is equivalent to factoring a number, such as factoring 81 into 9 into 9. That is, we have decomposed the value of 81 into 9 by 9. We can reconstruct the original matrix by doing the dot product of the decomposed matrices. The formula to do is matrix A is equal to P into L into U, where P is the parent matrix, L is the lower triangular matrix, and U is the upper triangular matrix. Eigen decomposition. It's a type of decomposition that involves decomposing a square matrix into a set of eigenvectors and eigenvalues. Singular value decomposition, also known as SVD. It's a matrix decomposition method for reducing a matrix to its constituent parts to make certain subsequent matrix calculations simpler. The formula is matrix A is equal to U into sigma into transpose of V, where U is M by M matrix, sigma is M by N diagonal matrix, and V power T is the transpose of N by N matrix. Now let's see in supervised learning what are the common problems solved. The common problems solved in supervised learning are 1. Regression, 2. Classification. The regression tries to predict results within a continuous output. The classification tries to predict results in a discrete output. Both regression and classification can exhibit linear and nonlinear behaviors. More on this in the latter part of the course. Types of linear regression problems. Univariate linear regression, that is ULR, predicts a single output value y from a single input value. Example, predict a person's weight given his or her height. Let's say we are given a data set that contains data for the heights and weights of individuals. We plot a line graph with the heights and weights on the x-axis and y-axis respectively. From this line graph, we can find out the weight for any given height, like this. In this regression problem, the dependent variable y depends on only one independent variable in x. Hence, it is called the univariate linear regression problem. The equation for ULR is, here, y is the dependent variable, x1 is the independent variable based on which y will be predicted, b0 is y-intercept, which is a constant term, then b1 is the slope coefficient for the independent variable. Multivariate linear regression, MLR. MLR predicts a single output value from a number of input values. Example, predict the house price given the location, the total square feet, the number of bedroom, hall, kitchen, and the number of bathrooms. Let's say we are given a data set that contains data for predicting house prices. The independent variables are location, total square feet, number of bedroom, hall, kitchen, and the number of bathrooms. The dependent variable is the house price. We plot a line graph with the independent variables and the dependent variable on x-axis and y-axis respectively. From this line graph, we can find out the house price for any given location, square feet, BHK, and the bathroom. Like this. Hence, it is called the multivariate linear regression problem. The equation for MLR is this. Here, y is the dependent variable, x1, x2, and so on till xn are the independent variables based on which y will be predicted. b0 is the y-intercept, which is a constant term, and b1 through bn are the slope coefficients for the independent variables, and epsilon is an error term. Now let's see the types of classification problems. There are 4 different types of classification problems, and they are binary classification problem, multi-class classification problem, multi-label classification problem, and imbalanced classification problem. Binary classification. Predict one output between 2 categories, that is answering simple questions with yes or no, true or false, 1 or 0. Example, will the customer renew the service? The answer could be yes or no. Multi-class classification. Predict one output between several categories, that is answering complex questions with one from multiple possible answers. Example, what fruit is this? And the answer could be any one of the available list of fruits. Multi-label classification. Predict multiple outputs between several categories, that is, answering complex questions with multiple from multiple possible answers. Example, what is the genre of the movie? And the answers could be suspense, horror, and romance. imbalanced classification. A classification dataset with skewed class proportions. Example, cancer versus non-cancer patients. Only a fraction of the total number of patients may be cancer patients. This is an example of imbalanced classification. With this, I'll conclude this video and I'll see you in my next video, Statistics Overview.